Hey folks, welcome to Hanneman Chapter 7. Uh, this is part one of two parts of lectures for Hanneman Chapter 7, Basic Ideas of Statistical Inference. All right, now all this information is the crux of pretty much everything in statistics, okay? Uh, this is why statistics exist. This is why it has such value to us. And again, I've told a few classmates, I've told a few of your classmates that, where you are right now in your intellectual development, it's kind of difficult to see how all this stuff is useful, okay? Um, and uh, but I'm convinced that as you go further into your studies, and as you have much more exposure to data, to research, to methodological issues, as you go along, I think you'll start to see why this stuff is so important and what it allows us to do as researchers, okay, as behavioral scientists, as social scientists, as epidemiologists. It has wide applicability, and it's important for you to sort of see that. But again, you'll probably that seeing it will develop over time. All right. Let's just go ahead and get going because we got a little bit to cover. Okay. All right. So just to give you a little sense of how these two lectures are going to be organized, or at least what their foci will be. Uh, this first one will talk about the big problem and then talk about the four major ideas, not the four. I mean, we could include others, but four big ideas in probability theory that allow us to address that big problem. Okay. Uh, the first part is more theoretical in nature. The second part will be more methodological in nature. All right, so we'll talk about what statistical inference is, and we'll talk about some of the methods that are used to make inferences. Okay. So we'll talk about sampling distributions, we'll talk about point and interval estimation, and the proper interpretation of those. Uh, on the interpretation, right, in classes like this one, you tend to get um, one type of interpretation of interval estimates. Um, and it's not quite technically correct, right? So we'll talk about the technically correct way to interpret these confidence or these intervals, all right? These different estimates that we have, all right? All right. So the objectives for this lecture are as follows, okay? Uh, of course, over in the lecture learning objectives, we have learn the vital role of statistical inference in scientific research. All right, hopefully you'll see that certainly by the time you finish the short lab for Chapter 7. All right, and of course review some of the major ideas in probability theory, which is what we're going to cover in just a few minutes. Uh, and then create a SAS app to compute and display interval estimations. All right. So um, we're going to do a little bit of that, but I've had to make some modifications. But anyway, you'll see, and you'll see how everything works. Okay. All right. Let's go to the next one. All right, so there are a number of key terms that we'll cover. The ones in light gray will be covered in part two. The ones in black will be covered um, in this first lecture. Okay. All right. So we'll talk about the central limit theorem, which is like one of the most important of all ideas in statistics, certainly when it comes to inference. Okay. We'll start with the expected value of a statistic. And then we'll talk about things like independent samples and law of large numbers, right? And then, review some stuff you already know, like, population parameters and so on and so forth. Okay. All right, so let's go ahead and jump into the big problem. We've talked about this a few times during the semester. Um, but I want to make sure that even if you're not fully understanding what the big problem is at this time, I want to sort of drill it into your head, right? So that when you get into your later courses and as you see these things more and more often, right, this big problem will become much more apparent to you and will become much more intuitive to you, right? All right. Uh, so inference, right? This is why we do statistics. Okay. Uh, the definition is basically this: using data from a sample to draw a conclusion about the population from which the sample was drawn. Okay. All right. Graphically, we can put it like this: we have our sample here. Okay. And now the question becomes, well, how well does this sample match up with the realities of the population, right? Now think about what realities means, what reality means, all right? So in this case, we're talking about the sum total of all the experiences, all the perceptions, all the behaviors, all the desires that everyone in this well-defined population has, right? All the characteristics of these folks, right? Um, and again, it's sometimes it's very, very difficult to get complete data on the population, right? And of course, that would be the best thing for us to do, right? If we want to understand this population, well, then we want to go to every single person in that population and ask them about what their experiences are, what their beliefs are, and things like that. Okay? And that will give us a perfect sense of, how this population or what um, uh, comprises reality for this population. All right. But of course, again, the big question is, does this sample reflect these realities that we would find in the population? All right. So in a more mathematical expression, we could say it like this. All right. Um, when we talk about whether or not the sample statistic matches up with the realities of the population, the problem we're talking about is error. Okay. The difference between the sample and the population. Okay, and of course we want error to be zero, right? We want our sample to perfectly match up with the realities that we would see in the population. Okay, so in this case, we take a sample statistic, and ideally, we want that sample statistic to have the exact same value as the population parameter. Okay, but like I said, uh, in the vast majority of cases, we don't know what this population parameter is. And since we don't know what this is, well, we can't compute this. Okay? So then how do we get around this problem of determining how well our sample statistic reflects the realities of the population. Okay. All right. In other words, are we getting good estimates or poor estimates of what the population looks like based on our sample? Okay. Good estimates or poor estimates? Right? Is our sample overall a good sample or is it a poor sample overall? How do we make sense of those questions? How do we answer those questions, right, in the absence of the population parameter? All right, so everything we talk about, right, all the theory we're about to cover, right, helps us address that problem. How to know whether or not you have a good estimate or a poor estimate, or a good sample or a poor sample without knowledge of the population parameter. Okay? All right. So here's what I've just stated writ large. Okay? All right. So we need to estimate the population parameter based on a sample that has an unknown quality. Okay. All right. Again, and that quality is, so is it a good sample or a bad sample? Okay. So once again, we have to rely on some of these key theoretical principles. All right. And as we'll talk about in the second part, statistical methodology. All right. So here we're going to talk about expected value, confidence, randomization, law of large numbers, and the central limit theorem. When we talk about methodology, statistical inference, sampling distribution, point estimation, interval estimation. Okay. All right. Now, just to kind of drive home the importance of this, uh, folks, um, you know, you got if you're going to do well in your future courses in statistics and research methodology, you have to understand these ideas. Okay, you have to understand these ideas. All right. So at the end of the semester, if they're still kind of fuzzy, just try to keep them in mind. Okay, as you go forward. All right. Read, start reading research. Okay. Maybe talk to your professors in your major. Okay. Please don't be afraid to do that. All right. Talk to your professors in your major. Talk to to your teachers, right? The people who are teaching, specific courses you're taking. Go talk to them and ask them about research, and then ask them, whether or not you can help them out with your research. All right, with their research rather. Okay. All right. So let's start with expected value. All right. So the expected value, as I have here, is a probable or predicted value of the true population parameter based on the sample statistic. Okay, so again, remember, we don't know exactly what that population parameter is. So we're predicting what that value is based on what we see in the sample. Okay. A more formal definition here for a random variable, the expected value, and so that could be the mean or the standard deviation, right? The median, the mode, right? Is the sum of each value of the variable multiplied by its proportion of all observations. Okay, so it takes into account the proportion, or rather, or you could say it otherwise. It takes into account the probability of seeing that value, right, in the sample, and from that we extrapolate to the population. So we say that even though we don't know what the true population parameter is, we expect that it's this value. All right. All right. So when we're looking at the calculation of the expected value, and again, folks, you don't have to worry about calculating these things by hand. SAS does all this for you. All right. But if we're looking at a mean, right? If we're looking at the expected value based on the mean, right? You would do this, you would calculate the expected value in a couple of different ways, right? Depending on what type of variable you're working with. All right, so if you're working with a discrete variable, right? So a discrete variable is a variable whose values are integers, right? They are whole number values. So 1, 2, 3, 4, so on. Okay. So if you have a discrete variable, you would take the probability, you would take the value of the variable, so represented here by x1, you would take the value of the variable and then multiply that value times the probability of, or the proportion of times that value occurs in the distribution, all right? Or in other words, the probability of observing that value in the distribution. Okay. All right, now for a continuous variable, we have to do this in a slightly different way. All right, and here's where if this course was being taught over in the math department, here's where you would start digging into methods of calculus. Okay, integration, limits, and things like that. Okay. So again, you don't have to worry about that. And SAS is going to take care of all that for you, and I'll show you how to get SAS to compute these things. Okay. One of the key terms here, and I think I asked you a question about this on the quiz. I'm pretty sure it's on there. All right. The expected value of a continuous variable is calculated using what's called a probability density function. All right, so let's go to the next slide and take a look at what that is. All right, so mathematically, this is what it looks like. A probability density function is a mathematical function used to calculate the probability between two values of a continuous variable. Okay. Now the probability between two values of a continuous variable, the probability of some value falling between two values of a continuous variable. All right. Graphically, it would look something like this. Okay, and we have an example here, but the example is essentially showing you the end result of applying integration to this. Okay. All right. So again, you don't have to worry about the mathematics. All right. But the graphic tries to illustrate what a density function looks like. Again, it refers to the area. Okay. It refers to the area under the curve. All right, so if we had two values, 0.5, 0.5, and 1.5, let's say that 0.5 is represented by x equals a, and let's say that 1.5 is represented by x equals b. All right, then when we compute this density function, right, we get a value of 0.75. All right, so this 0.75 means that 0.75 of the entire distribution falls between, right, x equals a, or x equals 0.5, okay, and x equals b. or in this case, x equals 1.5, right? So it's saying that 0.75 or 75% of the entire distribution falls between this point and this point, okay? So that's the reason why we call it a density function. So it's looking at the concentration of observations between any 2 points under the curve, all right? All right, so when we talk about an expected value, all right, now we sort of take out sample statistic and we insert this, the term, the expected value, okay? So now the question becomes, as I highlighted there in blue, without a known population parameter, how can we have any confidence that our expected value predicts or represents the population parameter? All right, so now everything we talk about from here on out, all right, at least for part one, all right, all the theoretical stuff we cover for the rest of part one of this lecture, right, is going to deal with that issue. Okay. All right. So let's think about, uh, when we say an expected value is representative of the population. Okay. All right. So there's certain key characteristics we look for in that expected value, right? In order for us to say, all right, yeah, this looks like it might be representative of a population, even though we don't know what that population parameter is. All right. It's equal to the true population parameter or closely approximates the true population parameter. All right. And very critical is this last one. Its standard deviation is 0 or something close to 0. All right. So I'll have some graphics later on to show you to try to help illustrate both of these points and how these two things really do go together. All right. All right. So one thing we can do to sort of build our confidence in our expected value, right, and build our confidence in stating that the expected value does represent the population parameter. A few things we can do, and a few things we can rely upon, right? The first thing is randomization. Okay. Second thing is law of large numbers. And then, like I said, the last thing is the central limit theorem. Okay. All right. So randomization. All right. Select, the definition is as follows. Selecting elements of a population. All right. So those elements can be people, animals, things, ideas, whatever. All right. Such that each element has the exact same chance of being selected into the sample. All right. So essentially what this means, I'll tell you what, let's go through the next slide. I was going to say essentially what this means is that randomization reduces bias in selection. Okay. All right. So in other words, you're not necessarily selecting people based on a certain set of characteristics they have. All right. Uh, or rather, I should say it like this, right? Um, you're not selecting you're making sure that a person is not selected into the sample based on some set of arbitrary characteristics. Okay. So let's say, I don't know, you're trying to find people to, uh, fill out a survey that you have. Okay. All right. Uh, so if we want it, if, well, I'll start it like this. I'll say, as an example of bias in selection, let's say that, all right, let's say this. You have your, survey in hand and you go out to some public square, right? And you need to ask, I don't know, let's say 100 people, right? The questions on your survey, and you need to get their responses. Okay. So what if, if a mother with a cute baby comes by and you say, oh, well, you know what? She looks like a really nice person. I think I'm going to ask her these questions, right? Versus, oh, that guy over there, man, he looks kind of like, thuggish. I think maybe I'll just stay away from people like that, right? All right. Well, again, if the mother with the cute baby is part of the same population as the, quote unquote thug, right? Then you've just biased your sample in a very significant way. Okay. By, just, you know, deliberately taking the mother with the cute baby because she's a mother with the cute baby, right? Right. You want the choice of these folks making it into your sample based purely on, probabilities. Okay. Random probabilities. All right. So here on this slide, like I say, like I have here, all right, the major effects, not the only effects, but the major effects of randomization are as follows, right? Randomization will help us reproduce the shape of a variable's distribution in the population. Okay. And in gear 2, you're going to go through a demonstration of that. All right. Um, it also reduces bias in expected values. All right. So bias meaning that um, the any degree that the expected value is off, either less than or larger than the true population parameter. All right. And then it also minimizes standard deviation. All right. So it tends to not only get us close, right? So think about it. Randomization tends not only to get us close to the population parameter, right? But it gives us a sample that's pretty tightly clustered around it. Okay? All right. So those ideas are important. You want to keep those in mind, right? So reduces bias and then also gives us a pretty tight clustering of observations in our own sample around the true population parameter. Okay. All right, so when we talk about it reproducing the shape of a distribution, uh, here's just an example I worked up. All right. So in the big box here with the blue outline, all right, here we have the actual population. So this is a pretty small population of just 3,000 people. All right, and in the population we have a mean of 9.89 with a standard deviation of 9.37. Okay. All right. So here we take, in this first sample, right, we take only 1% of the sample. So here we're working with 30, right? We're working with a sample size of 30, right? Uh, and even with such a small sample, we get some numbers that they're off, but not way, way far off. So we have 7.85 for a mean and 9.5 for a standard deviation. So the mean is off by 2 points, okay, which is still unacceptable. It's not a huge difference, but it's, we want the population mean, right? That's what we want. All right. The standard deviation is a little bit closer to the population standard deviation. So, that's good, right? But again, we want it to be exactly the same. All right, so what do we do? Well, one thing we can do is increase the sample size. So here um, we go from 30 to 150. All right. So in this sample of 150, we have a mean that this time overshoots the population parameter. All right, and the standard deviation also overshoots the population parameter. Okay. All right. But then as we go from 150 to 300, right, we start to see a little more of a closure, right, between our sample statistics and our population parameter, right? Just a little more of a closure there. Okay. So the mean is 10.03, right, versus a mean of 9.89, right? A standard deviation of 10.54 compared to the population standard deviation of 9.37. Okay. So what would happen as we get larger, as we take larger random samples from the population, what's going to happen is that our mean for our sample, the standard deviation for our sample, is going to get closer and closer and closer to the true population parameters. Okay. All right. So here's what I meant by bias. Okay. And just to kind of give you a couple of terms here. Right? So in the first example, all right, so the darker distribution, the darker bell curve represents the population. The one in the light gray represents the sample, and this is the expected value. Okay. All right. So in both cases, we have bias. Okay. But in this first case, we have negative bias. So this means that the expected value from the sample is less than the true population parameter. Okay. Here we have positive bias, right, which only means that the sample, the expected value for the sample, overshoots, right, the true population parameter, right? So here it underestimates the population parameter, negative bias. With positive bias, it overestimates the population parameter. Okay? All right, so as you get into your upper level classes, and again in statistics and research methods, you're going to come across these terms, probably more so than anything else, right? You're going to hear a lot about bias, right? Bias in the data, bias in this, bias in that. And, it always means that, some aspect or some characteristic of the population is being underestimated or overestimated by the sample. Okay. Okay. So the first big theoretical concept that we need to talk about. I mean, the really, really big ones now. All right. The first one is the law of large numbers, which states the following. If we randomly draw many independent samples from the same population, the mean of the sample means will approximate the expected value of the population parameter. All right, so you want to take into account a couple of things here. You want to think about a couple of things here. All right, so first of all, we're still only talking about the expected value of the population parameter. We're not talking about the actual value because, again, we don't know what that is, right? We don't know what that value is. So we're still just talking about the expected value. All right, let's go back up top here for a second. The mean of the sample means. All right. So, uh, you know, remember, we're looking at many independent samples. All right. So for the mean of the sample means simply translates into the mean of all these, means taken from the independent samples. All right. So we take the mean of each of these samples, and then we compute a mean of those means. Okay. All right. So one of the, if we go down below here, one of the major mechanisms of the law of large numbers is regression to the mean. All right. So this simply means that uh, as we keep drawing observations from a population, we're we're more likely to pull observations from those areas of the distribution where the concentration of observations is heaviest. All right, so if you think about a normal curve, right, most observations are concentrated in the middle. Okay, so if we pull, you know, if we randomly pull observations from that distribution, right, there's always going to be a much higher probability that we pull observations from the middle of that distribution, right? And there's going to be a lower probability of pulling observations from the tails, right? From the tails of the distribution, right? But again, right, as we make more and more observations, we tend to move closer and closer to that expected value of the population parameter. Okay. All right. So let's go to what I hope is going to be a clarifying graphic for you. Okay. All right. Uh, so here's just a restatement of regression to the mean. But let's take a look at. Let me try to explain to you what's going on in this graphic. All right. Um, Now, since this is simulation, we can set up a population mean. Okay. All right. And so here the population mean is 0, 0.0. Okay. All right. Now, what's going on here is that we start with a sample of 1 right here. All right, and we go up to a sample of 500. Okay, so when we start with some of the smaller samples, right, we tend to get these when we start with the smaller samples, and then we calculate the mean for those samples, all right, or the mean of the sample means. Here's what happens. Okay, we tend to get values of the sample mean that swing pretty wildly and kind of far away from the true population mean. Okay. All right. So let's see, this would probably be a sample of 2 people here, right? This sharp point that falls way down here. All right. So in these smaller sample sizes, we get some pretty, again, radically different values for our mean. Okay, radically different in terms that they fall pretty far from the true population mean. All right, but look at what happens as we add more and more people. Okay, right? As we add more and more people, you get less and less variation around the true population mean. Okay, so every time we compute a mean, a new mean, as the sample gets larger, that mean tends to fall much, much closer to the true population mean. All right, so our sample means, the mean of our sample means, you could say, all right, tends to fall much, much closer to the true population mean. Okay, and when we get out here to the upper ranges, right, the amount of variation or the amount of difference between our expected value, right, based on the mean of the sample means, and our population parameter, right, gets even closer, right? Both of those things get even closer to each other. Okay. So again, you can see some difference, right? But the difference is minimal. Minimal. All right. That's the whole goal. Right? That is the whole goal. To get to this point, to get to samples, right, that look like this. Right? Where we take the mean, and if we were able to compare it to a known population parameter, even though the sample mean might not be the exact same as the population mean, but it would be pretty damn close. I mean, real close. All right, where the difference between the two, right, is really close to zero. That's what we're always going for. That's what we always hope for. Okay. Is there anything else I need to say about this? I think that's it. Uh, what's here? Oh, yeah, I forgot. Need to say just a word or two about this. All right. Again, I think there is a question about this on the quiz. All right. So you have two versions of the law of large numbers. You have the weak law of large numbers, and you have the strong law of large numbers. All right. And once you read the definitions, it kind of makes sense. All right. The weak law essentially says that the expected value never, ever uh, is never ever exactly equal to the population parameter, the true population parameter, right? You can keep pulling samples as large as you want, but you never get to the true population parameter. Whatever statistic you get from your sample, it's either going to overshoot or undershoot. All right, it's going to overestimate or underestimate the true population parameter. Okay, all right. So there's always going to be some non-zero difference between the sample mean and the true population mean. Okay. The strong law of large numbers says no, it's going to converge, right? That as you pull more and more samples, right? As you pull more and more samples from the population, right? The mean, or the expected mean, rather, right? So the sample mean, the expected mean, will converge, right, towards the true population mean, and therefore the difference between our expected mean and the true population mean will become zero. In other words, think about the equation I showed you before. Error equals the difference between the sample statistic and the population parameter. Okay? So the weak law of large numbers says that difference is always going to be larger than zero. Okay? It might be very small, but it's always going to be larger than zero. All right? The strong law says no. Nope. It's going to converge and it's going to become zero. Right? So the weak law of large numbers, error is always going to be larger than zero. Right? The strong law of large numbers, error will eventually reach zero. Okay? All right. Yeah, one more thing here about the law of large numbers. I think this is the last slide for the law of large numbers. Okay? And again, this is something you want to keep in mind. Okay? Randomization drastically reduces bias in estimation. All right? So if we were to go back to that graphic where you see that jagged line shooting around the true population mean, okay? What happens, right? So in those smaller samples, you get a lot more variation around the true population mean. Okay, right? But as you get into larger and again randomly drawn samples, right, you start getting very, very, small differences between the sample mean and the population mean, which means you're reducing bias. Okay, you get a lot less bias. Okay. All right. The central limit theorem. If we didn't have this, if we couldn't establish this idea, well, you probably wouldn't be taking a course in statistics. Okay. But the big reason why you're taking this course in statistics is because, a lot of you are going to be working with a lot of data. I spoke to one of your classmates who is majoring in consumer affairs. Um, he will spend a lot of time looking at data, okay? And he's going to spend a lot of time doing this type of work, okay? And pretty much every time he says, all right, well, this is what we see. This is the level of consumer confidence in our sample. Um, every time he tries to say that what we see in our sample is probably reflective of the population, he is relying upon the central limit theorem, okay? Heavily upon really all of these ideas, but certainly the central limit theorem. All right, so why do we need this central limit theorem? Well, like we have here, randomization and the law of large numbers, it gives us some confidence, right, in addressing the big problem. All right, again, how do you know your sample represents the population parameter? All right. Um, and we say that like right here, the law of large numbers assume we can add an infinite number of observations to our sample. All right. Well, that's just not in the realm of possibility. We can't just keep doing that. Okay. We have a limited amount of resources that we can use to grab observations from different folks in our population, right? Usually, uh, and if you look at even at the studies done by these huge universities, right? Rich, like Harvard rich, $50 billion in endowment, right? Uh, even these big universities, typically when they conduct surveys of the population, it's one sample, right? All right, just one sample. Okay. So in that case, randomization, again, randomization helps us, law of large numbers helps us, but we really can't reproduce, you know, the law of large numbers, the actual process of testing the law of large numbers in actual data. Okay. Another problem is that randomization and law of large numbers doesn't say much about the characteristics of the population. All right. Uh, uh, you know, do these things perform better only in a population with a normal distribution, or will they perform just as well in a population with a non-normal distribution, with some crazy distribution. Okay. All right. And then the last big point here. Okay. Neither randomization nor the law of large numbers give us a guideline for evaluating our sample in the absence of a known population parameter. Okay, and again, remember that's like the big problem, right? So since we don't know the population parameter, we don't know how much error we have in our sample. Therefore, we can't say whether or not the sample statistics that we get are good estimates or poor estimates, all right, of the population. All right. So we need to develop something that says, all right, we can rely on this statistical process, right? This element of probability theory, right? We can rely on this thing, right, to help us answer that question, whether or not we have a good or poor sample. Okay. All right. So what does the central limit theorem state? All right. The CLT states that if we draw many independent samples of sufficient size from the same population using a random selection method, the distribution of sample means will approximate a normal distribution around the true population parameter. All right, and then for the big point here, regardless of the actual shape of the population distribution. All right, so now think about what that means. It means that even if you don't know what the population looks like, right, which also means you don't know the population parameter, right? So even if you don't know what the population looks like, it doesn't matter. It doesn't matter. All right? You can still pull a sample out of that population, or, in this case, multiple samples out of that population. All right? And those samples, if we take the mean of each of those samples, that collective set of means will form a normal distribution around the true population parameter. Okay? Hey, seriously, folks, without this class wouldn't exist. And I know some of you are probably thinking, oh, wow, that would be just too bad, Dr. Davis. Yeah, well, if you feel that way, screw you. But, seriously, this I really do hope you understand it at some point, in your intellectual development, your time here at Long Beach State. I seriously hope that you get to a point where you say, oh, yeah, see, this stuff really does help me understand what's going on in the world, right? It really does. It really has the power to do that, and it's incredibly valuable. Okay. All right. So let's move on. Just have just a few more slides here. All right. Um, I'll run through this very quickly. Um, but you'll do this. You're going to do this for gear 2. All right. And you're going to be using data based on on the population here at Long Beach State. Okay. Again, because we always need a well-defined population. Well, all right. Well, we certainly have one here. All right. So we're going to use it. We're going to develop this test of the central limit theorem. All right, based on an analysis of the population here at Long Beach State. Okay, so just a few steps here. You want to create a population with a random variable. Okay, draw multiple independent samples of the same size. All right, from that population. Find the mean of each sample. Right, normalize the distribution using the z-score method. All right, so we covered that in chapter 6, right, the z-score method. So that equation that was used in chapter 6 is the same equation we're talking about. Well, not the exact same equation, but I'll say roughly the same. Okay, roughly the same. You would be able to recognize what's going on if you saw it. Okay, and then you plot the distribution with a histogram, plot the probability density curve. All right, and those two things should match up, right? So the histogram should take on a normal distribution. Maybe it's not perfectly normal, but it should be normal, right? Oh, and a couple other things here. All right, so on the quiz, I'll ask you about the definition of independent samples. So these are samples drawn repeatedly and randomly. All right, samples drawn repeatedly and randomly from a population are independent if at least one person in each sample is unique. Okay, uh, so if we start with this first sample of 5 people, all right, in the second sample we can have 4 of these 5, right, but we have one person that's different. Okay, so this sample would be considered independent from this one. Okay. Here's the equation for the normalization method, and you see it kind of looks like the z-score method that you used in chapter 6. Okay, but again, this is something you're not going to have to calculate by hand. You're going to tell SAS, do this, and it will do it for you. Okay. This is just an example I put together. All right. And just to kind of show you graphically what the central limit theorem talks about, was what it's trying to, convey to us, right? So we start with a population distribution. And again, this population, this is what you would call a uniform distribution, right? Almost every observation, almost every value in the distribution has the exact same proportion, okay? All right. Uh, so not the exact same, but they're pretty close together. All right. So uh, so it's clearly not a normal distribution. Okay. But if we pull, uh, I think I pulled what, uh, 500 samples. Right. I pulled 500 samples out of this population and then just plotted them, right, using a histogram. And this is what I get. Okay. We have the bars representing the actual means. Okay. And then we have the red line here representing the probability density function, or a probability density curve for a normal distribution. All right, you can see it matches up pretty well. It's not an exact match, but it matches pretty well. Okay. All right. So when we get into the second part of this lecture, all right, we'll dig a little bit more into this sampling distribution, all right, and talk about what it means for us as researchers who have only a single sample from the population. Okay, it helps us out quite a bit. All right. All right. One other thing here about the central limit theorem that you would find in pretty much every textbook in statistics. It's called the empirical rule. And one of the key characteristics of a normal distribution, perfect normal distribution, and when you're thinking about the central limit theorem, right, is that, as we have here, 68% of all observations will fall within plus or minus 1 standard deviation of the mean. 95% within plus or minus 2 standard deviations. 99.7% of observations will fall within plus or minus 3 standard deviations. All right, so over here we have the distribution for those 500 samples that I pulled from that population, that uniform distribution. Okay, and what we get is something that looks, again, just a lot like a normal distribution. Okay, all right. We have 68% of the samples that fall within plus or minus 1 standard deviation of the mean. We have 95%, okay, that fall within plus or minus 2 standard deviations, and 99.7% that fall within plus or minus 3 standard deviations. One way you can tell that it's not a perfectly normal distribution is that you have a couple of observations on the outside. All right, so outside of this 99.7. All right, so that indicates here that it's not a perfect normal distribution, but it's pretty close. Okay, pretty close. All right, so again, to kind of wrap this up, and I know I've said this before, but again, I'm trying to kind of, burn this into your brains. Okay. All right. So when we think about how the CLT helps us with that big problem, since we don't know the true population parameter, we can't make a direct inference from the sample to the population. All right. Instead, we should focus on how well the methodology used to select the sample, randomization, sample size. All right. We want to focus on how well that performs. All right. In terms of getting us close to the true population parameter. Okay. All right. Let's see. What is next? I can't remember what I put next here. Oh, there we are. So the CLT says if the sample of sufficient size is randomly selected from a population, then we can safely state any of the following. There's a 68% chance our sample statistics fall within plus or minus 1 standard deviation of the true population mean. Again, even if we don't know what that true population parameter is, we know based on the central limit theorem that what we see in our sample, if it's randomly drawn from the population and of sufficient size, okay, if it's randomly drawn from the population and it's of sufficient size, we can say there's a 68% chance our sample statistics fall within plus or minus 1 standard deviation of the true population parameter. There's a 95% chance that what we see in our sample falls within plus or minus 2 standard deviations of the true population parameter. Okay? And lastly, there's a 99.7% chance that our sample statistics fall within plus or minus 3 standard deviations of the true population parameter. Okay. All right. Let's think. All right. That's it for lecture 1. Okay. I know that was a long lecture, but this stuff is important. Okay. So certain things should be reiterated. Certain things we should kind of take our time on. And I want you to please, folks, when you get to the quiz for Chapter 7, okay, some of it's going to be theoretical, and then some of us, of course, are going to get into SAS. All right, please do not hesitate to contact me. All right, when you take a look at the questions, and if you need some clarification on something, or whatever, okay, just contact me. I'll happily help you out. Okay. All right. So you want to make sure you watch the second lecture video. All right. And then you want to do the lab assignment before you get to Gear 2. All right. So if you do those two things and then you go to Gear 2 should be pretty straightforward for you. Okay. All right, I'll see you in a little while.